Hello and welcome to the Snoozy Scientist. I'm very glad you found your way here tonight. Before we get comfortable, tell me where you're listening from. Maybe you're tucked into bed with the lights turned low, stretched out on the sofa after a long day, or somewhere far away with the night still quietly unfolding outside. Wherever you happen to be, get comfortable, settle in, and give your mind a little room to wander. And if you enjoy these slow, sleepy journeys through science, you can help the channel along with a like and a subscribe. To everyone who has already done that, thank you. It genuinely means a great deal, and it helps these strange little corners of science reach a few more curious minds. Tonight, we're going to explore something that surrounds you every second of your life, yet becomes surprisingly difficult to describe the moment you ask what it actually is. Space seems simple enough. It is the gap between things, the emptiness between planets, stars, atoms, and even the particles inside atoms. But according to modern physics, that emptiness is not nearly as empty as it looks. Quantum fields extend through it, the vacuum has physical properties, and when we ask whether space itself is made from something even deeper, physics begins to reach the edge of what it currently understands. So make yourself comfortable, let the rest of the day fade quietly into the background, and we'll begin with a question that sounds wonderfully simple. What is space actually made of according to quantum physics? Space is one of those words that seems perfectly simple until we stop and ask what we actually mean by it. Most of the time, we use the word without much thought. Space is the distance between your chair and the wall. It is the gap between Earth and the Moon. It is the enormous emptiness separating one star from another. In everyday life, space feels like the background in which everything else happens. Objects occupy it, light travels through it, planets move across it, and we rarely need to wonder whether the space itself is doing anything at all. Physics makes that picture much stranger. Modern physics often speaks not simply about space, but about spacetime. Space and time are treated as parts of one combined geometric structure. This does not mean that distance and time are identical. Rather, measurements of where and when events occur are connected in a way that cannot be cleanly separated in the description of nature. That already makes the question of what space is made of rather unusual. If we ask what an ordinary object is made of, the question has a familiar meaning. Take a wooden table. We can break the wood into smaller structures. Those structures contain molecules. Molecules contain atoms. Atoms contain electrons surrounding atomic nuclei. Those nuclei contain protons and neutrons contain quarks. In modern particle physics, particles such as electrons and quarks are described through quantum fields. So when we ask what the table is made of, we are following a chain from large structures towards smaller physical ingredients. It is tempting to assume that we can do the same thing with space. Perhaps somewhere beneath everything we see, space is built from tiny pieces. Perhaps there is some microscopic grain of space, far smaller than an atom, waiting to be discovered. That possibility is studied seriously in theoretical physics. But it is not something that has been experimentally established. And this is where an important distinction becomes useful. There is a difference between asking what exists in space and asking what space itself is. Imagine removing everything from a region of space. Take away the stars, planets, dust, gas, atoms, and individual particles. At first it might sound as though what remains should simply be nothing. According to modern physics, that is not quite right. A region containing no ordinary particles can still be described using quantum fields. It can still possess a quantum vacuum state. It can still exist within gravitational geometry. and that apparently empty region can still have physical properties that matter when experiments are performed. So empty space is not the same thing as absolute nothingness. Absolute nothingness would mean no matter, no radiation, no fields, no geometry, and perhaps not even any meaningful idea of location or duration. Physics does not normally deal with that kind of philosophical nothingness. When physicists talk about a vacuum, they are usually talking about a physical state with very specific properties. That difference matters enormously. Quantum field theory describes matter and radiation using quantum fields that are defined throughout spacetime. The particles we observe can be understood as excitations of those fields. An electron, for example, is associated with an electron field. Light is described through the electromagnetic field. These fields do not disappear simply because a particular region contains no detectable particles. That makes empty space far richer than the old mental picture of a perfectly blank void. But there is a trap here. If quantum fields exist everywhere, it is easy to say that space must therefore be made of quantum fields. That conclusion does not automatically follow. A field can exist throughout space without being the substance from which space itself is constructed. In our established theories, quantum fields are usually described as existing within spacetime. Spacetime provides the geometric setting in which the fields are defined and evolve. General relativity adds another layer to the story. In general relativity, spacetime is not merely a rigid, invisible box sitting behind the universe. Its geometry is dynamical. Matter and energy are connected with changes in that geometry, and distances and durations can behave differently depending on the gravitational environment. So modern physics gives space a surprisingly active role. On one side, general relativity describes a dynamical spacetime geometry. On the other, quantum field theory describes a collection of quantum fields existing throughout spacetime, with particles appearing as excitations of those fields. Both theories are enormously successful within the situations where they have been tested. Yet neither gives us a complete, experimentally confirmed answer to the deepest version of the question. What is spacetime itself made of? We do not currently know whether that question will eventually have an answer similar to the answer for matter. Space may possess microscopic constituents. It may have some form of quantum structure. It may emerge from deeper relationships that do not resemble ordinary particles at all. Or it may turn out that asking what space is made of is slightly misleading, because space may not be a substance in the ordinary sense. This is where the problem of quantum gravity enters. Quantum field theory describes the quantum behavior of matter and the known non-gravitational interactions with remarkable precision. General relativity describes gravity and spacetime geometry with equally remarkable success on larger scales. But a complete theory that describes spacetime itself in fully quantum terms has not yet been experimentally established. That gap is where many of the most ambitious ideas in modern fundamental physics live. Some proposals suggest that spacetime could be discrete at extremely small scales. Others explore the possibility that smooth space emerges from something deeper. These are serious areas of research, but they must be kept separate from what experiments have already confirmed. So when we ask what space is actually made of according to quantum physics, the most accurate starting point is not a dramatic claim that physicists have discovered tiny atoms of space. The more interesting answer is that empty space is already much less empty than it appears. It contains quantum fields. It possesses a vacuum state. It exists within a geometry that can change and respond to matter and energy. And beneath all of that lies a deeper question that physics has not yet finished answering. Whether space itself has fundamental ingredients at all. For a long time, Space was treated almost like the quietest part of the universe. It was simply there, a vast, invisible stage on which everything else moved. In the 17th century, Isaac Newton built one of the most successful physical descriptions ever created, and within that description, space and time had a very definite character. Space was absolute. Time was absolute. Neither depended on the objects moving through them. You could imagine removing every planet, every star, every grain of dust, and every living thing from the universe, and Newtonian space would still remain. It would still provide locations. It would still provide directions. It would still provide distances between one empty point and another. Time would continue passing as well, quietly and uniformly, whether anything interesting happened or not. This was an extremely useful way to think about nature. Newton's mechanics described falling objects, orbiting planets, projectiles, tides, and countless other phenomena with astonishing accuracy. For centuries the picture worked so well that it became natural to think of space as a kind of invisible container. Objects could move through it, forces could act across it. But space itself did not need to do very much. Not everyone was satisfied with that idea. One of Newton's great intellectual rivals, Gottfried Wilhelm Leibniz, argued for a very different view. Leibniz questioned whether absolute space was actually necessary. Instead of imagining space as an independent thing that existed all by itself, he suggested that spatial relationships between objects were more fundamental. A position only had meaning because of how one object was related to another. A distance was a relationship. A direction was a relationship. From this perspective, empty space without anything in it became much harder to define. If there were no objects at all, what exactly would distinguish one supposedly empty location from another? This disagreement between Newton and Leibniz was not merely philosophical decoration. It raised a question that would return again and again in physics. Is space a thing in its own right, or is it somehow defined through relationships between physical objects? For a while, Newton's practical success gave the absolute picture enormous influence. Then, during the 19th century, something new entered physics. Field's Michael Faraday played a major role in changing how physicists imagined the supposedly empty regions surrounding matter. Faraday studied electricity and magnetism and developed the idea of lines of force extending through space. A magnet did not simply influence another magnet mysteriously from a distance. An electric charge did not merely reach across emptiness and pull on another charge. Instead, Faraday treated the region surrounding these objects as possessing physical structure. Electric and magnetic effects were represented through fields extending through space. This was a profound change. The empty stage was beginning to acquire properties. James Clerk Maxwell pushed the idea much further. During the 19th century, Maxwell developed the mathematical theory that unified electricity and magnetism. His equations showed that changing electric fields and changing magnetic fields could generate one another. Even more remarkably, the resulting electromagnetic disturbance could travel through space as a wave. When Maxwell calculated the speed predicted for these waves, it matched the measured speed of light. The implication was extraordinary. Light itself was an electromagnetic wave. Visible light, electricity, and magnetism were all parts of the same underlying physical theory, and electromagnetic waves could travel through regions containing no ordinary matter. That created an uncomfortable question for 19th century physics. If light was a wave, what exactly was waving? Water waves involve water. Sound waves in air involve changing pressure in air molecules. Waves on a rope require a rope. so it seemed natural to assume that light must also be travelling through some hidden medium. Physicists called this hypothetical substance the luminiferous ether. The ether was imagined as something filling all of space. It had to be strange stuff. It needed to carry light over enormous astronomical distances, yet apparently offer no noticeable resistance to planets moving through it. It had to be extremely rigid in one sense, because light travelled so quickly, while being almost completely undetectable in another. Nature was apparently being asked to provide an invisible cosmic material with a rather demanding job description. If the ether really filled space and remained stationary while Earth travelled through it, then Earth should move through the ether much as a boat moves through water. That motion ought to affect measurements of the speed of light. Albert Abraham Michelson and Edward Williams Morley designed an exceptionally sensitive interferometer experiment to search for this effect. Their famous experiment compared light travelling along different directions as Earth moved through space. If the planet were travelling through a stationary ether, light moving along Earth's direction of motion should behave slightly differently from light travelling across it. The expected ether wind was not detected. The result did not instantly destroy every possible ether theory, but it became an important part of a growing problem. The old mechanical picture was becoming increasingly difficult to maintain. Then Albert Einstein changed the discussion completely. In 1905, Einstein introduced the special theory of relativity. Instead of trying to preserve a hidden mechanical medium for light, special relativity began from a different set of principles. The laws of physics should take the same form for observers moving uniformly relative to one another, and the speed of light in vacuum has the same value for every such observer. That second statement sounds innocent until its consequences are followed carefully. If different observers must agree on the speed of light, then they cannot always agree on ordinary measurements of distance and time. Lengths can depend on relative motion. Durations can depend on relative motion. Two events that one observer regards as simultaneous may not be simultaneous for another observer moving relative to the first. Space and time could no longer remain completely separate, rigid backgrounds. The luminiferous ether was no longer required as a preferred mechanical medium carrying light. Electromagnetic fields did not need to be interpreted as vibrations of some invisible cosmic material. This is an important lesson whenever we ask what space is made of. Physics has repeatedly discovered entities that exist throughout space without concluding that space itself must be made from an ordinary substance. The electromagnetic field is real in the physical sense that it carries energy, momentum, and produces measurable effects. But it is not a fluid secretly filling a classical container. That old expectation came from trying to force new physics into familiar mechanical imagery. By the beginning of the 20th century, the supposedly empty stage had already become much stranger. Space could contain fields even when it contained no matter. Light could cross a vacuum without requiring a material ether. Measurements of distance and time depended on motion in ways Newton's absolute background had never allowed, and physics was only just beginning to discover how dramatic the change would become. Long before quantum theory transformed the vacuum into something even more unfamiliar, empty space had already stopped looking empty. By the early 20th century, the old picture of space as a rigid and universal background was already beginning to unravel. Albert Einstein's special theory of relativity had shown that different observers could disagree about measurements that once seemed absolute. Two observers moving relative to one another could measure different lengths. They could measure different amounts of elapsed time. They could even disagree about whether two distant events happened at exactly the same moment. And yet both observers could still describe the laws of physics correctly. The key was that the speed of light in vacuum remained the same for every inertial observer, regardless of their own motion. This forced space and time into a much closer relationship than classical physics had allowed. A few years later, Hermann Minkowski found an especially elegant way to express that relationship. Minkowski had once been one of Einstein's mathematics teachers, and he realized that special relativity could be understood geometrically. Instead of thinking about 3 dimensions of space evolving separately through an independent flow of time, Minkowski combined them into a single 4-dimensional structure. Spacetime. Every event could now be described not only by where it happened, but also by when it happened. 3 coordinates describe its location in space. A 4th coordinate describes its position in time. The separation between events depends on both. This did not mean that time simply became another ordinary direction like left and right. Time plays a distinct role in the geometry. But treating space and time together made the strange effects of relativity much more natural. Time dilation and length contraction were no longer isolated tricks of moving clocks and rulers. They became consequences of the geometry of spacetime itself. Even here, spacetime was not being treated as a material substance. There were no spacetime molecules floating about. There was no need to imagine a transparent fabric made from microscopic threads. Spacetime was the geometric framework describing relationships between events, particles, and light. Then Einstein made that framework even more remarkable. In his general theory of relativity, completed in 1915, spacetime stopped being merely the fixed geometric setting of physics. Its geometry became dynamic. Matter and energy could influence the shape of spacetime, and that geometry could influence how matter and light moved. Gravity was no longer described simply as an invisible force reaching across empty space. Instead, free-falling objects followed the natural paths available within curved spacetime. One of the ideas guiding Einstein toward this description was the principle of equivalence. Imagine being inside a sealed lift. If the lift were resting on the surface of Earth, you would feel your weight pressing you against the floor. But if the lift were far from any planet and accelerating upward, you could experience something locally very similar. Conversely, if the lift were falling freely toward Earth, objects inside would appear weightless alongside you. Einstein recognized that this deep relationship between acceleration and gravity could be used to understand gravity geometrically. The result changed the status of space once again. Spacetime could curve, clocks could run at different rates depending on the gravitational environment, light could bend as it travelled near massive objects. The orbit of Mercury, which had contained a small unexplained shift in the orientation of its closest approach to the Sun, could be described accurately by general relativity. Gravitational lensing could magnify, stretch, and distort images of distant galaxies as their light passed through curved spacetime around intervening matter. These are not merely visual metaphors for a mathematical theory. They are measurable effects. A clock placed deeper within a gravitational field runs more slowly relative to a clock higher up. Modern atomic clocks are sensitive enough to measure gravitational time differences over remarkably small changes in height. And spacetime can do more than remain quietly curved around matter. Its geometry can carry waves. General relativity predicts that accelerating masses can produce gravitational waves, propagating disturbances in spacetime geometry that travel at the speed of light. For decades, their direct detection remained extraordinarily difficult because the changes they produce are tiny by the time they reach Earth. That changed in 2015. The Laser Interferometer Gravitational Wave Observatory directly detected a gravitational wave produced by the merger of 2 black holes more than 1 billion light-years away. the passing wave changed the lengths of the observatory's perpendicular arms by an incredibly small amount, allowing scientists to measure a disturbance that had travelled across the universe. It was a striking demonstration that spacetime geometry is not simply a passive coordinate system drawn over reality. It can evolve, it can curve, it can ripple, and those changes can be measured. Yet there is an important limit to what this tells us. General relativity is still a classical theory. It describes spacetime as a smooth geometry. It does not tell us whether that geometry has quantum states, microscopic constituents, or some deeper structure at extremely small scales. So by the time quantum physics enters the story in full, space is already nothing like Newton's silent and unchanging stage. It has become part of the physical drama itself. The remaining mystery is whether this flexible geometry is fundamental, or whether even space-time is only the large-scale appearance of something deeper. Quantum physics did not arrive by announcing that space itself was made of something new. Instead, it began by changing our understanding of the things that occupy space. At the end of the 19th century, physicists were struggling with a seemingly simple problem involving heat and light. A hot object emits electromagnetic radiation. As its temperature rises, the colour and intensity of that radiation change in predictable ways. Classical physics could describe parts of this behaviour, but it failed badly at short wavelengths. Max Carl Ernst Ludwig Planck found a way through the problem. In 1900, Planck proposed that energy exchanged between matter and electromagnetic radiation came in discrete amounts. These packets were related to the frequency of the radiation through a new fundamental constant, now known as Planck's constant. At first, this was partly a mathematical solution to a troublesome calculation, but the idea of quantization did not remain a mathematical curiosity for long. In 1905, Albert Einstein used a closely related idea to explain the photoelectric effect, in which light shining on a material can eject electrons from its surface. Einstein proposed that light transfers energy in individual packets, later called photons. Increasing the brightness of light could increase the number of these packets, but whether individual electrons were released depended on the frequency of the light, and therefore on the energy carried by each photon. Light had acquired a distinctly quantum character. Then matter began behaving strangely as well. Louis-Victor Pierre-Raymond de Broglie proposed that objects usually regarded as particles could also possess wave properties. An electron, in other words, should not always behave like a tiny billiard ball travelling along one definite path. Experiments involving electron diffraction and interference confirmed this remarkable prediction. Electrons could produce patterns associated with waves. The old distinction between particles and waves was beginning to dissolve. During the 1920s, Werner Karl Heisenberg and Erwin Rudolf Joseph Alexander Schrödinger developed two major mathematical formulations of quantum mechanics. Heisenberg created matrix mechanics. Schrödinger developed wave mechanics and introduced the wave function, which could evolve according to his famous wave equation. The two approaches looked very different, but physicists soon established that they were mathematically equivalent descriptions of the same quantum theory. The meaning of the wave function itself required another important step. Max Born argued that the wave function should not simply be interpreted as an ordinary physical wave spread through space like a ripple across water. Instead, it provides the information needed to calculate probabilities for possible measurement outcomes. Quantum mechanics therefore does not generally assign a particle one perfectly definite classical history that simply remains hidden until someone looks. An electron can occupy a quantum state in which its position is not sharply defined in the classical sense. When a position measurement is made, quantum theory predicts probabilities for the possible results. This is one reason that familiar pictures of tiny particles quietly following exact paths through empty space become unreliable at microscopic scales. Werner Karl Heisenberg's uncertainty principle made this departure even clearer. Position and momentum form one of the important pairs of quantities whose uncertainties are fundamentally related. Making the position of a quantum object increasingly well defined necessarily increases the spread of possible momentum values. This is not merely a problem caused by clumsy measuring equipment. It is built into the mathematical structure of quantum mechanics. Nature at this scale does not behave as though every object must always possess the complete set of sharply defined classical properties we might instinctively expect. And yet ordinary quantum mechanics still left an important limitation. In many basic quantum problems, we begin with a certain number of particles and continue describing those same particles as time passes. Relativity makes the situation more complicated. Energy can be converted into massive particles, and particles can disappear through interactions that produce other particles. A sufficiently energetic photon, under appropriate conditions, can contribute to the creation of a particle and its antiparticle. An electron and a positron can annihilate, producing photons. The number and type of particles present, therefore, cannot always remain fixed. A deeper framework was needed. That framework became quantum field theory. Quantum field theory combines quantum principles with special relativity and changes the emphasis dramatically. Instead of beginning with individual particles as the deepest ingredients of nature, it begins with quantum fields. Particles become particular excitations of those fields. An electron is associated with an electron field. A photon is an excitation of the electromagnetic field. Other fundamental particles are likewise connected with their corresponding quantum fields. This change becomes especially important when thinking about apparently empty space. If we remove every detectable electron from a region, the electron field does not have to disappear. If there are no photons passing through that region, the electromagnetic field has not ceased to exist. The absence of particles is not the absence of the underlying fields, and so the quantum view begins to turn the idea of emptiness inside out. Classically, we might imagine that removing all the particles leaves behind a blank region of space. In quantum field theory, removing the particles can still leave something physically meaningful behind. The fields remain. Their lowest energy state remains. And that means the empty space between visible things is no longer quite as empty as it first appeared. Quantum field theory takes one of the strangest ideas in modern physics and makes it central. The universe is not described as a collection of tiny particles moving through an otherwise empty background. Instead, the deeper description is built around fields. A field is something that has a value throughout space and time. Classical physics already contained familiar examples. The electromagnetic field can exist throughout a region of space, and its changing configuration can carry energy in the form of light. Quantum field theory takes this idea much further by combining fields with the principles of quantum mechanics and special relativity. The result is the framework used to describe the fundamental particles and interactions of modern particle physics. One of the major steps toward this framework came from Paul Adrian Maurice Dirac. Dirac developed a relativistic quantum theory of the electron that successfully combined important features of quantum mechanics with special relativity. His equation also led to a remarkable prediction. It implied the existence of a counterpart to the electron with the same mass but opposite electric charge. That particle, the positron, was later discovered experimentally. Antimatter had entered physics. This created a deeper difficulty for the idea that nature could always be described using a fixed collection of individual particles. Particles could be created. Particles could disappear. Matter and antimatter could be produced from energy under suitable conditions, and they could annihilate into other forms of energy. A theory that simply followed the motion of a permanent set of particles was no longer enough. Werner Karl Heisenberg, Wolfgang Ernst Pauli, Pascual Jordan, Paul Adrian Maurice Dirac, and several other physicists helped develop the early ideas that eventually became quantum field theory. The basic shift was profound. Instead of treating particles as the primary objects and fields as something secondary, quantum field theory treats fields as fundamental. Particles appear as excitations of those fields. An electron is therefore not best imagined as a tiny bead that exists completely independently of everything around it. It is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. Gluons arise from the gluon field associated with the strong nuclear interaction. Neutrinos are connected with neutrino fields. The particles involved in the weak nuclear interaction are excitations of their corresponding quantum fields. The Higgs particle is an excitation of the Higgs field. Together, these fields form part of the standard model of particle physics, the theory describing the known fundamental particles and 3 of the 4 known fundamental interactions. Gravity is the important exception. The standard model does not contain a complete quantum theory of gravity. The field picture changes how empty space must be understood. Suppose a perfectly empty region contains no electrons. That does not mean the electron field has disappeared from that part of the universe. It means the field is not in a state containing an electron excitation there. The same idea applies to photons. A dark region containing no detectable light does not mean the electromagnetic field has been removed. The field still forms part of the physical description. This distinction between a field and a particle excitation is essential. The field is not simply a cloud made from large numbers of particles. The particle is one particular way the field can behave. That is why saying that quantum fields fill the universe can be useful, but it also needs some care. The word fill can make the fields sound like ordinary substances poured into an empty container. That is not really the picture. A quantum field is not known to be a fluid, gas, fabric, or invisible material in the everyday sense. It is a fundamental part of the mathematical and physical framework used to describe nature. Its possible states are quantum states, and measurable quantities associated with the field are represented through quantum operators. That description may sound abstract, but its predictions are anything but vague. The standard model has been tested with extraordinary precision. Experiments at laboratories around the world, including the European Organization for Nuclear Research, have repeatedly confirmed predictions involving quantum fields. Particle collisions, particle decays, electromagnetic interactions, strong interaction processes, and weak interaction processes all fit remarkably well within this framework. The discovery of the Higgs particle in 2012 provided another major confirmation of the field-based description. Quantum fields are therefore not speculative decorations added to physics, because they sound mysterious. They are part of one of the most successful theoretical structures ever developed, and they give us an important clue about apparently empty space. A region can contain no ordinary particles and yet still be described by all of these underlying fields. The absence of particles does not leave behind an absence of physics, but one distinction must remain clear. Quantum fields existing everywhere does not prove that space itself is made from quantum fields. In the conventional formulation of quantum field theory, those fields are defined within spacetime. They occupy the stage, even if the stage is far stranger than Newton imagined. So when we look at an apparently empty region of the universe, quantum physics tells us that far more is present than our eyes could ever reveal. The fields remain. And even when none of them are excited into detectable particles, they do not simply vanish. Empty space in quantum physics is not simply the absence of everything. It has a state. That statement sounds strange at first, because we usually think of emptiness as the place where there is nothing left to describe. Remove the particles, remove the light, remove the matter, and surely the job is finished. Quantum field theory says otherwise. Every quantum field can exist in different possible states. Some states contain excitations that we recognize as particles, other states contain many particles. But even when there are no particles present, the field itself does not disappear. Instead, it can occupy its lowest possible energy state. This is what physicists call the quantum vacuum. The word vacuum can be slightly misleading because it sounds like a perfect absence. In everyday language, a vacuum means something has been removed. In quantum field theory, the vacuum is not the absence of the field, it is a particular state of the field. The lowest energy state available. So an apparently empty region of space can contain no detectable photons, electrons, quarks, or other particles, while the electromagnetic field, electron field, quark fields, Higgs field, and the other quantum fields still remain part of the physical description. This gives empty space a very different character from classical nothingness. A useful comparison comes from ordinary quantum mechanics. Imagine a quantum system that behaves somewhat like a tiny oscillator. Classically, the lowest energy state might seem obvious. The system would simply stop moving completely and sit perfectly still. Quantum mechanics does not generally allow such a simple picture. Certain pairs of physical quantities cannot both possess perfectly sharp values at the same time. Werner Karl Heisenberg's uncertainty principle is the familiar example. Position and momentum cannot both be fixed with unlimited precision. That means the lowest energy state of a quantum system is not necessarily equivalent to complete classical stillness. The same broad idea carries into quantum fields. A field in its vacuum state is not simply a classical field set permanently to zero everywhere. Its quantum state still possesses structure. One way physicists describe that structure is through correlation functions. A correlation function tells us something about how measurements associated with a quantum field at one location or time are related statistically to measurements at another location or time. Even in the vacuum state, these relationships do not generally vanish. Two separated regions can therefore possess quantum correlations even when no ordinary particles are present between them. This does not mean that empty space contains a hidden collection of little objects secretly travelling around. The structure belongs to the quantum state of the field itself. That distinction becomes increasingly important as quantum field theory becomes more realistic. It can be tempting to imagine one enormous thing called the vacuum stretching across the universe. The actual picture is more complicated. Different quantum fields have different properties. The electromagnetic field has its own quantum states. The electron field has its own. Quark and gluon fields participate in the strong interaction. The Higgs field has a particularly unusual vacuum structure because its lowest energy state possesses a non-zero field value. These fields also interact with one another. So the full vacuum of an interacting quantum field theory is not simply a pile of completely independent fields quietly resting side by side. Their interactions, symmetries, and possible ground states all matter. In some theories, the nature of the vacuum can even determine which symmetries are visible in the physical world. This is one reason physicists take vacuum structure so seriously. The vacuum is not merely an empty background chosen for convenience. It can influence measurable physics. At the same time, there is an important boundary to keep in mind. When physicists say the vacuum has structure, they are not saying they have discovered a new substance resembling air, water, or the old luminiferous ether. There is no need to imagine space filled with a transparent quantum mist. The vacuum is a quantum state. It is described using the mathematics of quantum fields, and its consequences appear through the way those fields interact with matter, boundaries, detectors, and one another. This also helps explain why the phrase absolute nothingness belongs more comfortably to philosophy than to ordinary quantum field theory. A quantum vacuum already assumes that there are fields. It assumes that those fields can occupy states. It assumes a space-time setting in which the theory is defined, so it is something very different from the complete absence of matter, fields, geometry, time, and physical law. If every detectable particle were removed from a region, quantum field theory would still have something meaningful to describe. The fields would remain in their vacuum state. Their correlations would remain. Their interactions would still be part of the theory, and measurable consequences could still emerge from that supposedly empty region. This gives us one of the clearest answers physics can currently offer to the question of what remains when ordinary matter is taken away. Not particles, not a mechanical medium, not a featureless void. A quantum vacuum. A lowest energy state of the fields that underlie the known particles and interactions. But even this does not tell us what spacetime itself is fundamentally made of. The quantum vacuum describes the state of fields within spacetime. Whether spacetime has its own deeper quantum ingredients is a separate and much less settled question. So empty space turns out to be far from empty. Even in its quietest possible state, the universe still has something to describe. One of the most surprising consequences of quantum physics is that even the lowest possible energy state is not necessarily completely still. A useful place to see this is the quantum harmonic oscillator. The classical version is simple to imagine. Picture a mass attached to a spring. Pull it away from its resting position and let go, and it oscillates back and forth. As energy is removed, the motion becomes smaller and smaller until, in the classical picture, it can simply stop. Quantum mechanics does not allow quite the same ending. The quantum oscillator has a lowest possible energy state, known as its ground state. But that ground state still has a small, non-zero amount of energy. This is called zero-point energy. The reason can be understood intuitively through Werner Karl Heisenberg's uncertainty principle. If the oscillator were perfectly motionless at one exact position, then both its position and momentum would be known with complete precision. Quantum mechanics does not permit that. The more sharply position is defined, the less sharply momentum can be defined, and vice versa. So the ground state settles into a compromise. It is the lowest energy state available, but not a state of perfect classical stillness. This idea becomes especially important in quantum field theory. A free quantum field can be mathematically decomposed into modes that behave in many respects like an enormous collection of quantum harmonic oscillators. Each mode has its own ground state contribution. So even when the field contains no particles, its lowest energy state can still possess quantum structure associated with these zero-point contributions. This is where the phrase quantum fluctuations often appears. Unfortunately, it is also where popular explanations can become a little too enthusiastic. Quantum fluctuations do not fundamentally mean that tiny particles are constantly popping into existence, wandering around briefly, and then disappearing again. That picture can sometimes be useful as a rough visual shortcut, but taken literally it is misleading. A more accurate description is that observables associated with a quantum field can have statistical spreads even in the vacuum state. The vacuum does not assign every measurable property one perfectly definite classical value. Instead, quantum theory predicts probability distributions and correlations. Those correlations can extend between different points in space and different moments in time. When fields interact with matter, boundaries, or other fields, this vacuum structure can contribute to effects that are physically measurable, so the fluctuations are not imaginary. But they are not best pictured as a miniature storm of little particles constantly erupting from nowhere. There is another complication. If every independent mode of a free quantum field contributes a zero-point energy, and there are infinitely many possible modes in the idealized theory, then simply adding all of those contributions together produces an infinite result. Clearly, writing down an infinite energy density and carrying on as though nothing unusual happened would not be very useful. Quantum field theory handles these expressions through techniques including regularization and renormalization. Regularization introduces a controlled way of dealing with formally divergent quantities so that the structure of the calculation can be analysed. Renormalization then relates the parameters appearing in the theory to physical quantities that are actually measured. It is sometimes described casually as physicists simply removing infinities because they are inconvenient. That description misses the point. Renormalization is a systematic framework that has been tested to extraordinary precision. It allows quantum field theory to produce finite, measurable predictions even when intermediate mathematical expressions contain divergences. In many situations, what matters physically is not an absolute zero-point energy by itself, but differences between configurations or the way quantum corrections affect observable quantities. This is one reason the quantum vacuum can have measurable consequences without automatically giving us a simple universal number for the total energy of empty space. The idea of virtual particles is closely related to another common misunderstanding. Virtual particles appear in perturbative calculation methods, especially in diagrams used to organize contributions to particle interactions. They are not ordinary particles that can be directly detected while briefly existing between measurements. They do not simply borrow energy from the universe and then hurriedly repay it before quantum mechanics notices. That familiar phrase is catchy, but it is not a precise description of the theory. Virtual particles are internal elements of a calculation. Real particles, by contrast, can propagate freely and be detected as physical states. Keeping those two ideas separate helps prevent the quantum vacuum from turning into something almost magical. The real picture is strange enough already. Even the lowest energy state of a quantum field has structure. It possesses uncertainties. It possesses correlations. And those properties can influence real physical systems. So empty space, viewed through quantum theory, is not a calm blank background in the classical sense. But neither is it literally a boiling soup of particles appearing from nothing. The quantum vacuum is subtler than either image. It is a ground state with genuine physical structure, quietly revealing that even emptiness has rules. One of the clearest ways to see that empty space is not simply nothing comes from an effect so delicate that it appears only when objects are brought extremely close together. It is called the Casimir effect. In 1948, Hendrik Brucht Gerhard Casimir predicted that two conducting surfaces placed very close to one another should experience a force. At first glance, that seems rather odd. Imagine two metal plates facing each other in a vacuum. No air between them. No obvious material connecting them. No classical spring pulling them together. And yet, under the right conditions, a measurable force appears. The explanation comes from the quantum electromagnetic field. Even when no photons are present, the electromagnetic field remains in its vacuum state. Now place two conducting plates close together. The plates impose boundary conditions on the electromagnetic field. Not every possible field configuration can exist between them in exactly the same way that it can exist outside them. A useful analogy is a guitar string. A string fixed at both ends can only vibrate in certain allowed patterns. The electromagnetic field is not literally a string, but the idea of restricted modes is helpful. Between two conducting plates, only certain electromagnetic modes are compatible with the boundaries. Outside the plates, a different set of modes is available. The difference between these allowed quantum field configurations changes the energy associated with the arrangement. The result is a force. For two ideal parallel conducting plates, that force is attractive. It also grows very rapidly as the plates are moved closer together. At separations of ordinary everyday size, the effect is far too small to notice. At microscopic and especially submicroscopic separations, however, it becomes much more important. For ideal parallel plates, the force per unit area increases roughly with the inverse fourth power of the separation. That means making the gap only a little smaller can make the force dramatically stronger. Actually measuring such a tiny effect is difficult. Marcus Sparnay carried out an early experimental investigation during the 20th century. His measurements were broadly consistent with the predicted effect, although the precision available at the time was limited. Much more accurate experiments came later. Stephen Lamoureux performed a high-precision measurement in the 1990s using conducting surfaces arranged in a way that made the force easier to detect. Umar Mohideen and collaborators later performed further precise measurements at very small separations. These experiments helped establish that forces of the predicted size really do appear. The Casimir effect is therefore not merely a thought experiment, it is a measurable consequence of quantum electrodynamics. But there is a subtle point here that is worth keeping clear. A very common explanation says that there are fewer vacuum fluctuations between the plates than outside them. The outside fluctuations therefore push harder, forcing the plates together. This picture can be useful as a first intuition, but it should not be taken too literally. The Casimir effect can also be described using the electromagnetic interactions and fluctuating responses of the charges inside the conducting materials themselves. Different mathematical approaches can arrive at the same physical prediction. That matters because the effect is sometimes presented as direct proof that empty space contains a literal ocean of zero-point energy pressing on everything around us. That conclusion goes too far. The experiment confirms quantum predictions involving electromagnetic fields, material boundaries, and the vacuum state. It does not require us to imagine empty space as being packed with tiny invisible particles battering the plates from both sides, nor does it show that spacetime itself is made from vacuum energy. The force also does not provide a route to unlimited free energy. If the plates move together because of the Casimir attraction, energy can indeed be released in the process, but separating them again requires work. Once the entire physical cycle is considered, there is no endless supply of energy appearing from nowhere. The universe, rather inconveniently for anyone hoping for a magical vacuum-powered machine, still keeps careful accounts. What makes the Casimir effect important is something quieter and more interesting. A region with no ordinary matter between two surfaces can still behave differently depending on the quantum state of the electromagnetic field and the boundaries placed around it. The supposedly empty gap participates in measurable physics. Its quantum description matters. That is a remarkable departure from the classical idea of empty space as a completely featureless absence. And yet the distinction remains essential. The Casimir effect tells us something real about quantum fields in empty regions. It tells us that the vacuum state is physically meaningful. It tells us that changing the conditions around a quantum field can change measurable forces. But it does not tell us that spacetime itself is built from virtual particles, zero-point energy, or electromagnetic waves. So the Casimir effect gives us one of the most elegant experimental hints that emptiness is not truly empty. Place two conducting surfaces close enough together, and a quantum structure associated with the space between them quietly makes itself known. Not with a flash, not with a burst of particles, just with a tiny force gently revealing that even a vacuum can have consequences. Hydrogen is the simplest atom in the universe, and for that reason it has often served as a kind of testing ground for our deepest theories of physics. One proton, one electron, and, in principle, not much room for confusion. Yet even hydrogen eventually revealed that empty space was doing more than anyone had first expected. Paul Adrian Maurice Dirac had developed a relativistic quantum theory of the electron that brought quantum mechanics and special relativity together with remarkable success. His equation naturally included electron spin and gave extremely accurate predictions for the energy levels of hydrogen. According to the theory, certain hydrogen states should have exactly the same energy. For a while that seemed entirely reasonable. Then experiment found something different. In 1947, Willis Eugene Lamb and Robert Curtis Rutherford carefully measured two closely related energy levels in hydrogen. Instead of finding them perfectly aligned, they discovered a tiny difference. One level was shifted slightly relative to the other. The difference was small, but it was real. And because hydrogen is so simple, even a tiny disagreement between theory and experiment mattered enormously. This became known as the Lamb shift. The measurement showed that Dirac's original treatment, impressive though it was not the complete story. Something else was affecting the electron. Part of the explanation came from treating the electromagnetic field itself quantum mechanically. Hans Albrecht Bethe produced an early calculation soon after the experiment and showed that interactions between the electron and the quantist electromagnetic field could account for much of the observed shift. The full modern explanation comes from quantum electrodynamics. Quantum electrodynamics describes the interaction between charged particles and the electromagnetic field using quantum field theory. It became one of the most precisely tested theories in all of science. Shinichiro Tominaga, Julian Seymour Schwinger, Richard Phillips Feynman, and Freeman Dyson all played major roles in developing and organizing the renormalized form of the theory. Within this framework, the electron inside hydrogen is not treated as though it exists in complete isolation from an otherwise blank vacuum. It is coupled to the quantum electromagnetic field. That interaction changes the energy levels slightly. One important contribution is called electron self-energy. The electron interacts with the electromagnetic field associated with its own quantum behavior, and that interaction modifies the energy attributed to the electron state. Another contribution comes from vacuum polarization. Quantum corrections alter the way the electromagnetic interaction behaves around the charged particles in the atom. Together with other radiative corrections, these effects shift the predicted energy levels by small amounts. The result is the Lamb shift. The important point is not that tiny particles are literally swarming around the electron like insects around a light bulb. That familiar image is too crude. The deeper statement is that the quantum state of the electromagnetic field affects measurable properties of the atom. Even when there are no ordinary photons present, the electromagnetic field remains part of the physical system. Its vacuum state matters. And hydrogen is sensitive enough for us to detect the consequences. The Lamb shift is small. For the famous transition measured in hydrogen, the frequency difference is on the order of roughly 1000 MHz. That is tiny compared with the much larger energy scales that determine the basic structure of the atom. But modern spectroscopy is precise enough to resolve such differences, and the agreement between detailed quantum electrodynamic calculations and experiment is extraordinary. This is one of the reasons the quantum vacuum is not merely a philosophical curiosity. Its effects show up in numbers that laboratories can measure. A closely related example appears in spontaneous emission. An atom can occupy an excited energy state and later release a photon as it drops into a lower state. In a simple classical picture, one might imagine that the atom simply decides to radiate because an electron is moving around. Quantum field theory gives a more precise explanation. The excited atom is coupled to the quantist electromagnetic field. That coupling allows the atom to make a transition to a lower energy state while creating a photon excitation in the field. So even the process of spontaneous emission depends on the fact that the electromagnetic field is present as a quantum field. The atom is never truly sitting alone in an utterly featureless void. This gives us another way to understand what physicists mean when they say empty space has physical structure. The Casimir effect shows that boundaries can alter quantum field behavior and produce measurable forces. The Lamb shift shows that the quantum electromagnetic field can subtly alter the internal energy structure of an atom. Spontaneous emission shows that excited atoms interact with the quantist field even when no incoming photon triggers the process. All of these phenomena point in the same broad direction. The vacuum is not simply nothing. It is a physical quantum state that can influence measurable systems. But once again, the distinction between fields and spacetime itself remains important. The Lamb shift tells us something about quantum fields existing within spacetime. It does not reveal tiny grains of space. It does not show that spacetime is built from electromagnetic fluctuations. It does not identify microscopic pieces from which distance itself is assembled. What it does show is already remarkable enough. Even the energy levels inside the simplest atom carry a faint imprint of the quantum fields that remain when everything appears empty. The quantum vacuum does more than subtly shift the energy levels inside atoms. It also changes the way electric charge itself appears to behave. That does not mean an electron suddenly becomes a completely different particle depending on where we look. The underlying electron remains the same. What changes is the effective strength of the electromagnetic interaction once the surrounding quantum fields are taken into account. This effect is known as vacuum polarization. To understand the idea, imagine an electron sitting quietly in space. Classically, we would describe the electron as producing an electric field around itself. The strength of that field becomes weaker with distance, but the basic picture is straightforward. Quantum electrodynamics adds another layer. The electron does not exist in isolation from the quantum electromagnetic field and the other quantum fields that interact with it. Those interactions produce small corrections to the simple classical picture. Physicists call these radiative corrections. Vacuum polarization is one of them. In perturbative calculations, the electromagnetic field around a charge can interact with contributions associated with the electron and positron fields. These effects alter the way another charged particle responds to the original charge. A common visual description says that the vacuum behaves a little like a polarizable medium. Around a negatively charged electron, quantum effects partly screen the charge when it is viewed from farther away. At shorter distances, that screening is reduced. The electron therefore appears to have a slightly stronger effective electric charge when probed more closely. This analogy is useful, but it should not be taken too literally. The vacuum is not filled with ordinary electron and positron pairs permanently arranging themselves like molecules inside a piece of glass. The underlying description comes from quantum field theory. In calculations, contributions involving electrons and positrons can appear as internal lines in Feynman diagrams. These internal objects are commonly called virtual particles, but virtual particles are not ordinary detectable particles secretly inhabiting empty space. They are elements of a mathematical expansion used to calculate the probability amplitudes of physical processes. This distinction matters because vacuum polarization is real even though the cartoon of physical particle pairs continuously appearing around every charge is not the fundamental explanation. The observable consequence is that the effective strength of the electromagnetic interaction depends slightly on the scale at which it is measured. This is known as the running of the coupling constant. A coupling constant tells us, in broad terms, how strongly a particular interaction operates. For electromagnetism, the relevant quantity is connected with the strength of the electric interaction between charged particles. At ordinary atomic distances, its value is extremely familiar and very precisely measured. At much shorter distances, or equivalently at much higher energies, quantum corrections cause the effective electromagnetic coupling to become slightly stronger. The change is small, but modern experiments can detect it. This means that what we casually call the strength of electromagnetism is not represented by one completely unchanging number at every possible scale. Quantum field theory predicts how that strength evolves. The effect is not unique to electromagnetism. The other fundamental interactions also have couplings that change with energy, although they behave differently. The strong nuclear interaction, for example, becomes weaker at extremely high energies, while the electromagnetic interaction slowly becomes stronger. Vacuum polarization also affects atomic physics. One important example is described by the Ewing potential, named after Edwin Albrecht Ewing. The Ewing potential represents a correction to the ordinary electric potential produced by vacuum polarization. In atoms, that small change slightly alters the energy levels experienced by electrons. These effects contribute to precision measurements such as the Lamb shift, and become especially important in systems where particles orbit very close to atomic nuclei. Because the corrections are tiny, they provide an unusually demanding test of quantum electrodynamics. A theory can appear successful when predicting large, obvious effects. Predicting tiny deviations correctly is much harder. Quantum electrodynamics has repeatedly passed these tests. Measurements of atomic spectra, scattering processes, magnetic properties of particles, and high-energy collisions agree with its radiative corrections to extraordinary precision. One of the most famous examples involves the magnetic behavior of the electron. Quantum electrodynamics predicts a tiny correction to the electron's magnetic moment, and the agreement between theory and experiment reaches an astonishing level of precision. That success tells us something important about empty space. The quantum vacuum is not merely philosophical language added around the mathematics. Its structure contributes to calculations that match real laboratory measurements. When one charged particle interacts with another, the surrounding quantum fields affect the result. The interaction is not simply the bare classical force between two isolated points. It is dressed by quantum effects. That word, dressed, is often used by physicists because the measured particle includes the influence of the quantum fields with which it interacts. So even the apparently simple question of how strongly one electron repels another carries a faint imprint of the vacuum. The closer we probe, the more clearly those quantum corrections become part of the answer. And yet this still does not mean that space itself is made from those corrections. Vacuum polarization tells us how quantum fields behave within spacetime. It reveals that the vacuum state participates in electromagnetic interactions. It shows that apparently empty regions cannot be treated as perfectly inert backgrounds. But it does not reveal tiny units of distance or microscopic building blocks of geometry. That deeper question remains separate. What vacuum polarization gives us is something more modest and perhaps more impressive. It shows that even the strength of one of nature's fundamental forces depends subtly on the quantum structure associated with empty space. The vacuum does not merely sit there. It quietly changes the way charged particles experience one another. The Higgs field is unusual even by the standards of quantum physics. Like the electron field or the electromagnetic field, it extends throughout the universe. But unlike many familiar fields, its lowest energy state is not associated with a field value of 0. Even apparently empty space contains a non-zero Higgs field. That makes it particularly important when asking what seems to remain after ordinary matter and radiation have been removed. During the 1960s, several physicists independently developed ideas that would become central to the modern understanding of the Higgs mechanism and electroweak symmetry breaking. Among them were Francois Englert, Robert Brout, Peter Ware Higgs, Gerald Stanford Guralnick, Carl Richard Hagen, and Thomas Walter Bannerman Kibble. Their work addressed a difficult problem. The mathematical theories describing fundamental interactions were built around symmetries. These symmetries were extremely powerful, but they appeared to require certain force-carrying particles to have no mass. That created trouble for the weak nuclear interaction. The particles associated with the weak interaction are very massive. So physicists needed a mechanism that could preserve the underlying structure of the theory while still allowing these particles to acquire mass. The Higgs field provided the solution. A useful way to understand what makes this field different is to imagine an ordinary field whose lowest energy configuration occurs when its value is 0. If nothing disturbs it, the field simply settles at 0 everywhere. The Higgs field does not behave that way. Its lowest energy state occurs at a non-zero field value. Physicists describe this by saying that the Higgs field has a non-zero vacuum expectation value. In the conventional energy units used in particle physics, that vacuum expectation value is approximately 246 gigaelectronvolts. This number does not mean that every tiny region of empty space contains a little packet carrying that amount of ordinary usable energy. It characterizes the background value of the Higgs field in its vacuum state, and because that value exists throughout space, particles can interact with the Higgs field everywhere they go. This is crucial for electroweak symmetry breaking. At sufficiently high energies, electromagnetism and the weak nuclear interaction are described as parts of a unified electroweak theory. As the universe cooled after its extremely hot early state, the Higgs field settled into its non-zero vacuum configuration. The underlying symmetry of the theory remained present in the equations, but the vacuum itself no longer displayed that symmetry in the same way. This is known as spontaneous symmetry breaking. Interactions with the Higgs field then allow the particles associated with the weak interaction to behave as massive particles. The electrically charged weak particles and the electrically neutral weak particle acquire mass through this mechanism. The photon remains massless. The Higgs field also interacts with fundamental matter particles through what are called Yukawa interactions. These interactions generate the standard model masses of fundamental fermions such as electrons and quarks. The stronger a particular fermion couples to the Higgs field, the larger the mass associated with that interaction. An electron couples relatively weakly and has a small mass. The top quark couples much more strongly and is vastly heavier. There is, however, an important limitation. The standard model includes the strengths of these Yukawa interactions as parameters that must ultimately be determined from experiment. It does not currently explain from first principles why the electron has precisely its observed coupling, while the top quark has another. So the Higgs mechanism explains how fundamental particles can acquire mass within the theory, but it does not explain every numerical mass value from some deeper principle. There is also an important distinction between the Higgs field and the Higgs boson. The field exists throughout space. The Higgs boson is a quantum excitation of that field. It is rather like the difference between an electromagnetic field and a photon, although the detailed physics is different. For decades, the Higgs boson remained the missing experimental piece of this picture. That changed in 2012. Two major experiments at the Large Hadron Collider operated by the European Organisation for Nuclear Research independently reported the discovery of a new particle with properties consistent with the Higgs boson. Those experiments were a toroidal Large Hadron Collider apparatus and the compact muon solenoid experiment. Further measurements have continued to support the identification of the particle as the Higgs boson predicted by the Standard Model. This discovery provided powerful evidence that the Higgs field is not merely a convenient mathematical invention. Its excitation can be produced and studied experimentally. Because the Higgs field extends throughout apparently empty space, it is tempting to take one more step and say that perhaps the Higgs field is what space itself is made of. That would be going too far. The Higgs field exists within spacetime in the Standard Model. It is not identified with spacetime geometry. If the Higgs field changed, the properties and masses of certain fundamental particles would change dramatically. But that does not mean distance itself would disappear, or that spacetime would cease to exist in the sense described by general relativity. The Higgs field is something present throughout space. It is not, according to established physics, the substance from which space is constructed. There is another common misconception worth clearing away. The Higgs field is often described as the source of mass. That is partly true, but only partly. It gives fundamental particles such as electrons and quarks their standard model rest masses. But most of the mass of ordinary matter does not come directly from those Higgs-generated quark masses. A proton contains quarks, but most of the proton's mass arises from the energy associated with the strong nuclear interaction, including the motion and confinement of quarks and the dynamics of gluon fields. The same is broadly true for neutrons. So even though the Higgs field plays an essential role in explaining why fundamental particles possess mass, it is not a universal reservoir from which all mass simply flows. Its importance is more precise than that. And for the question of empty space, its significance is especially striking. Remove the atoms. Remove the light. Remove every detectable particle you can. The Higgs field does not disappear. Its non-zero vacuum value remains part of the physical description. So apparently empty space contains yet another invisible but experimentally supported quantum field. But once again, something can exist everywhere without being what everywhere itself is made from. The Higgs field fills space. It helps determine the properties of matter, and yet space, at least in our established theories, remains something deeper and separate. The vacuum associated with the strong nuclear interaction is even more complicated than the electromagnetic vacuum. That is largely because the strong interaction behaves in a very different way from electromagnetism. The theory that describes it is called quantum chromodynamics. Quantum chromodynamics is the quantum field theory of quarks and gluons, the particles associated with the strong interaction. Quarks are fundamental particles found inside hadrons such as protons and neutrons. Gluons are the particles associated with the field that binds quarks together. At first glance, this may sound similar to the way photons are associated with the electromagnetic field. But there is an important difference. Photons do not carry electric charge. Gluons, however, carry the strong interaction charge themselves. That charge is called color charge. The word color here has nothing to do with visible color. It is simply the name physicists use for the type of charge involved in the strong interaction. Because gluons carry color charge, they can interact directly with one another. That makes quantum chromodynamics much more nonlinear than quantum electrodynamics. The gluon field can influence itself. And this self-interaction plays a major role in the strange behavior of the strong force. David Jonathan Gross, Hugh David Politzer, and Frank Anthony Wilczek helped establish one of its most important properties. It is known as asymptotic freedom. At extremely short distances, or equivalently at very high energies, the strong interaction between quarks becomes weaker. Quarks begin to behave more like nearly free particles. This was a remarkable discovery because it explained why high-energy scattering experiments could sometimes probe quarks almost as though they were loosely interacting objects inside protons. At larger distances, the behavior changes dramatically. Instead of weakening, the strong interaction becomes strong enough that isolated quarks are not normally observed. This phenomenon is called confinement. Quarks and gluons remain bound inside color-neutral combinations such as protons, neutrons, and other hadrons. Trying to pull two quarks apart does not simply weaken the connection between them. The energy stored in the strong interaction field grows. Eventually, enough energy can be concentrated to create new quark and antiquark combinations, producing additional hadrons rather than leaving one isolated quark behind. So the strong interaction is weak at very short distances and powerful at ordinary hadronic scales. That unusual behavior makes its vacuum state correspondingly rich. The low-energy vacuum of quantum chromodynamics is not well described as a collection of completely independent field oscillators. The strong interaction becomes too intense for the simplest perturbative calculation techniques to work reliably. Physicists refer to this regime as non-perturbative. Among the important features associated with the low-energy strong interaction is spontaneous chiral symmetry breaking. In an idealized limit where certain quark masses are treated as extremely small, the equations possess an approximate symmetry related to the left-handed and right-handed components of quark fields. The vacuum does not preserve that symmetry in the same simple way. Its structure helps produce important features of the hadrons we observe. The effects of the strong interaction vacuum are deeply connected with the fact that ordinary matter has the masses and properties it does. A proton contains 3 valence quarks, 2 up quarks and 1 down quark. It might seem natural to assume that the proton's mass is simply the sum of the masses of those 3 quarks. It is not. The rest masses of the up and down quarks account for only a small fraction of the proton's total mass. Most of the proton's mass arises from the energy associated with strong interaction dynamics, the motion of quarks, the gluon fields, and the complicated quantum behavior of the confined system all contribute. Through the relationship between mass and energy, that internal energy appears as most of the proton's mass. This is one reason quantum chromodynamics is so important for understanding ordinary matter. Almost all of the mass in familiar atomic nuclei ultimately reflects strong interaction energy rather than simply the Higgs-generated masses of the quarks inside them. Calculating this behavior is difficult. At low energies, the strong interaction is too intense for many ordinary perturbative methods. One of the major tools physicists use instead is lattice gauge theory. Kenneth Geddes Wilson played a central role in developing this approach. In lattice quantum chromodynamics, spacetime is represented mathematically as a grid. Quark and gluon fields can then be studied numerically on this discretized structure using powerful computers. This has allowed physicists to calculate quantities such as hadron masses with impressive agreement with experiment. But the lattice must not be misunderstood. The computational grid is a mathematical technique. It does not mean that experiments have discovered that physical space is literally made from tiny cubes. As calculations are refined, physicists study what happens as the lattice spacing is reduced toward the continuum limit. The grid is part of the method, not confirmed evidence for microscopic tiles of reality. That distinction brings us back to the wider mystery. The vacuum associated with quantum chromodynamics is extraordinarily rich. It reflects interacting quark and gluon fields. It is connected with symmetry breaking. It helps determine the structure and mass of the matter around us. And yet none of this tells us that spacetime itself is made from quarks, gluons, or a hidden lattice. Once again, empty space contains far more physical structure than its appearance suggests. But the quantum fields inhabiting that space are still not the same thing as space itself. The quantum vacuum becomes even more mysterious when we stop looking at atoms and particles and instead consider the universe as a whole. General relativity allows empty space to have a gravitational effect of its own. This possibility appears through something called the cosmological constant. Albert Einstein introduced the cosmological constant into his gravitational field equations during the early development of general relativity. At the time, the universe was widely assumed to be static, but gravity naturally tends to make matter attract other matter, which made a permanently static universe difficult to maintain. Einstein added the cosmological constant as a term that could counteract this tendency and help produce a stationary cosmic model. The situation changed once observations established that the universe is expanding. The cosmological constant was no longer required for Einstein's original purpose. But the idea itself never disappeared from the mathematics. And decades later, it returned in a remarkably important way. During the late 1990s, two research teams were studying distant exploding stars known as Type I supernovae. These supernovae can be used as powerful distance indicators because their brightness can be standardized well enough to compare their apparent brightness with their intrinsic luminosity. Researchers including Saul Perlmutter, Brian Paul Schmidt, and Adam Guy Ries were using these explosions to investigate how the expansion of the universe had changed over cosmic time. The expectation was fairly natural. Matter attracts matter gravitationally. So even though the universe was expanding, gravity should gradually slow that expansion. The observations revealed something unexpected. The expansion of the universe appeared to be accelerating. Distant galaxies were not merely continuing to separate because of an initial cosmic expansion. On very large scales, the expansion itself had entered an accelerating phase. The name given to whatever is responsible for this behavior is dark energy. The simplest widely used cosmological model describes dark energy using a cosmological constant. In that description, empty space possesses an approximately uniform energy density whose gravitational effect drives accelerated expansion. Dark energy accounts for roughly 2/3 of the present cosmic energy budget. Ordinary matter, including stars, planets, gas, people, and everything made from familiar atoms, contributes only a small fraction. Dark matter contributes most of the remaining matter component. This creates a particularly strange picture. As the universe expands, ordinary matter becomes increasingly spread out. Imagine a fixed amount of matter distributed through an ever larger volume. Its average density falls. Radiation becomes diluted as well, and its wavelengths are stretched by cosmic expansion, reducing its energy density even more rapidly. A cosmological constant behaves differently. Its energy density remains approximately constant as space expands. So if the volume of the universe increases, there is correspondingly more total energy associated with that constant density. This sounds deeply peculiar from an everyday perspective, but general relativity does not require cosmic energy accounting to behave exactly like energy conservation in a fixed, non-expanding background. The geometry of spacetime itself is dynamical. And this is where quantum field theory enters the puzzle. Quantum fields possess ground states. Those ground states have quantum structure. Free quantum fields can be described in terms of modes with zero-point contributions. So it is natural to ask whether the cosmological constant might somehow be connected with the energy of the quantum vacuum. At first, the idea sounds beautifully simple. Quantum theory says the vacuum has energy-related structure. General relativity says a constant energy density associated with empty space can influence cosmic expansion. Perhaps they are simply two descriptions of the same thing. Unfortunately, the numbers create a serious problem. If zero-point contributions from quantum fields are estimated in a straightforward way, and gravity is assumed to respond to those contributions directly, the resulting vacuum energy can be enormously larger than the value inferred from cosmological observations. The size of the disagreement depends on exactly how the estimate is constructed. A famous version of the argument produces a mismatch of around 120 orders of magnitude. That number is often described as one of the largest disagreements between a naive theoretical estimate and an observed physical quantity anywhere in science. But it needs some care. The exact number depends on assumptions about the highest energy scale included in the calculation, and on how the vacuum energy is estimated. There is no single calculation that universally produces precisely 120 orders of magnitude in every formulation. The deeper difficulty remains regardless. Quantum field theory seems to allow contributions to vacuum energy that are vastly larger than the extremely small cosmological constant compatible with the observed universe. This is known as the cosmological constant problem. It sits directly at the uncomfortable meeting point between quantum field theory and gravity. Within ordinary particle physics, many absolute energy offsets can be ignored because only energy differences affect non-gravitational experiments. Gravity is different. In general relativity, energy contributes to the gravitational behavior of spacetime, so an apparently arbitrary vacuum energy cannot simply be dismissed without asking how gravity responds to it. And yet the universe clearly has not curled up under an unimaginably enormous vacuum energy density. Something about the relationship between quantum vacuum energy and gravity remains poorly understood. Dark energy, therefore, should not simply be described as the zero-point energy of all the quantum fields in the Standard Model. That identification has not been established. The observed acceleration may indeed be explained by a cosmological constant, But why that cosmological constant has the value it does remains an open question. There are also alternative possibilities for cosmic acceleration, although none has displaced the cosmological constant as the simplest description. The important point is that the universe itself appears to be telling us that empty space and gravity are connected in a way we do not yet fully understand. At microscopic scales, quantum field theory gives us an extraordinarily successful description of vacuum structure. At cosmic scales, general relativity tells us how the energy content of the universe influences spacetime. When those two ideas are brought together, a profound mismatch appears. So the mystery of empty space is no longer confined to tiny experiments between metal plates or subtle shifts inside hydrogen atoms. It stretches across the entire observable universe. The quantum vacuum has measurable structure. Cosmic expansion is accelerating, and somewhere between those two facts lies one of the deepest unresolved problems in modern physics. Empty space becomes stranger still when motion and gravity are added to the picture. Until now, it has been tempting to imagine that the vacuum is one particular state of the quantum fields, agreed upon by everyone everywhere. In many simple situations, that picture works well enough, but quantum field theory reveals that the distinction between vacuum and particles can depend on how an observer is moving and on the geometry of the spacetime in which the fields exist. This becomes especially important when quantum fields are studied in curved spacetime. Quantum field theory in curved spacetime is an intermediate framework between ordinary quantum field theory and a complete theory of quantum gravity. The matter fields are treated quantum mechanically. The spacetime around them, however, is still described classically using general relativity. This approach is not expected to be the final description of nature, but it produces some extraordinary results. One of them is Hawking radiation. During the 1970s, Stephen William Hawking studied quantum fields around black holes. Classically, a black hole possesses an event horizon, a boundary beyond which light cannot escape to distant observers. Anything crossing that horizon continues inward. Nothing travelling slower than or equal to light can simply turn around and return through it. Hawking discovered that once quantum fields are considered, the situation changes. A distant observer can detect radiation associated with a black hole. This radiation has an approximately thermal spectrum, meaning it resembles radiation from an object with a particular temperature. The temperature is known as the Hawking temperature. For an ordinary astrophysical black hole, that temperature is extremely low. A black hole with roughly the mass of the Sun would have a Hawking temperature of only around 60 billionths of a Kelvin. More massive black holes are colder still. The effect is therefore far too weak to be directly detected from known astrophysical black holes with present technology. Yet the theoretical result is enormously important. It connects quantum field theory with gravity, thermodynamics, and the geometry of horizons. Hawking radiation is often explained using a picture in which a pair of virtual particles appears near the event horizon. One falls into the black hole while the other escapes. This can provide a rough visual story, but it should not be mistaken for the fundamental derivation. The real calculation concerns quantum fields in the curved spacetime produced by the black hole, and how different notions of particle states are related. The idea of a particle itself turns out to be less universal than it appears. A similar lesson emerges even without a black hole. Stephen Arthur Fulling, Paul Davies, and William George Unruh developed results associated with what is now called the Unruh effect. Imagine one observer moving freely at a constant velocity through otherwise empty space. That observer can describe a quantum field as being in its vacuum state. Now imagine another observer undergoing constant acceleration through the same region. The accelerating observer can describe the field very differently. An idealized detector moving with constant acceleration can respond as though it were surrounded by thermal radiation. The greater the acceleration, the higher the associated UNRA temperature. For accelerations familiar in everyday life, the predicted temperature is unimaginably tiny. An acceleration comparable with the gravitational acceleration near Earth's surface corresponds to an UNRU temperature vastly below anything that could easily be measured. To obtain even a temperature of roughly 1 Kelvin would require an acceleration of approximately 10 to the power of 20 meters per second squared. So no warm glow should be expected simply because an ordinary car has pulled away rather quickly from the traffic lights. But the principle is profound. One observer can regard a field as being in its vacuum state, while an accelerating detector responds as though particles are present. This does not mean that one observer is right and the other is hallucinating. The concept of a particle in quantum field theory depends partly on how field excitations are defined relative to time and motion. In simple flat spacetime, inertial observers share a particularly natural definition. For accelerated observers or observers in curved spacetime, different natural descriptions can emerge. The vacuum therefore cannot always be treated as a universally obvious state that every possible observer must identify in exactly the same way. This does not make physics subjective. Observers can still make consistent predictions about what their detectors will measure. The different descriptions are connected mathematically. What changes is the way the quantum field is separated into what one observer calls particles and what that observer calls vacuum. Horizons make this especially striking. A uniformly accelerating observer possesses an acceleration horizon, a boundary beyond which certain events can never send signals to that observer. A black hole possesses an event horizon created by spacetime geometry. In both cases, horizons affect how quantum fields are described. This is why the UNRA effect and Hawking radiation are closely related conceptually, even though their physical settings are different. They reveal that geometry, motion, and quantum fields cannot always be treated as completely independent ingredients. What appears to be empty space depends in part on the observer and the spacetime structure surrounding them. That is a much deeper statement than simply saying that particles occasionally appear in a vacuum. The vacuum itself is a quantum state whose interpretation can depend on the physical setting. And yet there is still an important limitation. In these calculations, spacetime remains classical. The geometry can curve, produce horizons, and influence quantum fields, but the geometry itself has not yet been given a complete quantum description. Hawking radiation and the UNRA effect therefore sit close to one of the most interesting boundaries in modern physics. They show what happens when quantum fields encounter acceleration, curved geometry, and horizons. They reveal that even the meaning of empty space can become observer-dependent. But they stop just before answering the deeper question. What happens when space-time itself must become quantum too? At this point, one tempting answer seems to be waiting for us. Perhaps space is simply made of quantum fields. After all, quantum fields are everywhere in the modern description of nature. The electron field extends throughout space-time. So does the electromagnetic field. The Higgs field has a non-zero value even in its vacuum state. Quark and gluon fields remain part of the theory even where no proton or neutron is present. It sounds almost irresistible to conclude that these fields are the substance of space itself, but established physics does not quite say that. In conventional quantum field theory, fields are usually defined on a space-time background. That distinction is subtle, but important. Imagine drawing a map. The map provides locations and relationships between those locations. Rivers, roads, forests and cities can then be placed on it. Quantum field theory works in a somewhat comparable way, although the real mathematics is far richer. Spacetime provides the structure that tells us how events are separated, which events can influence others, and how distances and durations are related. Quantum fields are then defined throughout that spacetime. The electron field tells us about possible electron excitations. The electromagnetic field describes electromagnetic phenomena and photons. The Higgs field helps determine the masses of several fundamental particles. The quark and gluon fields describe the strongly interacting ingredients of hadrons. These fields are physically real in the sense that their behavior leads to measurable predictions. But existing everywhere does not automatically make something identical with space. Temperature can be defined throughout a room, but the room is not made of temperature. An electromagnetic field can extend across a region, but the region is not automatically made of electromagnetism. The analogy is imperfect, because quantum fields are far more fundamental than temperature, but it helps expose the logical step that can easily be skipped. A field being defined everywhere is not the same as the underlying geometry being constructed from that field. The distinction becomes more interesting once gravity is included. General relativity tells us that spacetime is not simply an unmoving stage beneath the fields. Energy and momentum affect spacetime geometry. A star contains matter and radiation. The energy and momentum associated with that physical content contribute to the curvature around the star. That curvature then influences how planets move, how clocks tick, and how light travels. So fields influence geometry. Geometry, in turn, influences fields. An electromagnetic wave travelling near a massive object follows the curved spacetime around it. Quantum fields evolving near a black hole respond to the gravitational geometry there. The relationship is therefore two-way. But two things influencing each other does not mean that one must be made from the other. The surface of the ocean affects the motion of a boat, while the boat can also disturb the water beneath it. That interaction does not make the boat and the ocean the same thing. Likewise, quantum fields and spacetime geometry are deeply connected without established physics identifying them as one substance. This is one of the places where the Standard Model reaches its boundary. The Standard Model gives us an extraordinarily successful quantum description of the known matter particles and of the electromagnetic weak and strong interactions. What it does not provide is a complete quantum theory of gravity. There is no experimentally confirmed Standard Model field that can simply be pointed to and declared to be the microscopic substance of spacetime. Gravity remains described most successfully by general relativity, where it appears as the geometry of spacetime itself. That leaves us with two spectacular theories. Quantum field theory describes quantum matter and interactions. General relativity describes gravity and dynamic spacetime geometry. Each works beautifully in its own domain, but they do not yet merge into one experimentally established microscopic description of space. A thought experiment helps make the distinction clearer. Imagine removing every ordinary particle from a region. No electrons, no photons, no quarks bound into atoms, no detectable matter or radiation at all. Quantum field theory would not become empty. The electron field would still exist in its vacuum state. The electromagnetic field would still possess a vacuum state. The Higgs field would still retain its non-zero vacuum expectation value. The remaining Standard Model fields would still be part of the theory. So removing particles does not remove quantum fields. Now imagine, purely conceptually, removing those non-gravitational quantum fields from the description as well. In an ordinary quantum field theory formulated on a fixed background, the space-time structure on which those fields were defined would still remain mathematically. There would still be relationships between locations and times. There would still be a geometry. This shows why quantum fields and space-time are separate ingredients in the conventional framework. Of course, nature may turn out to be deeper than that framework. A future theory might reveal that space-time emerges from quantum degrees of freedom. Geometry might arise from entanglement. Space could possess discrete quantum structure. What we currently call fields and what we currently call space-time might eventually emerge together from something more fundamental. Those possibilities are taken seriously, but they are possibilities, not experimentally established conclusions. So saying that space is made of quantum fields is a little too strong. A more accurate statement is that what we casually call empty space is permeated by quantum fields and described by a vacuum state with measurable physical consequences. Those fields can influence particles. They can affect atomic energy levels. They can produce forces between boundaries. Their interactions change with scale. Their vacuum structure is connected with some of the deepest questions in cosmology. None of that is speculative. What remains uncertain is whether space-time itself has microscopic building blocks at all. Perhaps it does. Perhaps its geometry is fundamentally quantum. Perhaps smooth space is only what something deeper looks like when viewed across large distances. Or perhaps asking what space is made of will eventually prove to be the wrong kind of question. For now, physics can answer one part with great confidence. Empty space is not empty. Quantum fields remain even when particles are gone. The harder question is whether those fields live within space-time, as our established theories say, or whether some deeper theory will eventually reveal that space-time and quantum physics arise together from a more fundamental level of reality. Quantum gravity may be where the deepest version of this entire question finally has to be answered. So far, modern physics has given us two extraordinarily successful descriptions of nature. General relativity describes gravity through the geometry of space-time. Quantum theory describes matter, radiation, and the other known fundamental interactions through quantum states and quantum fields. Each framework works remarkably well. The difficulty appears when nature demands both at once. General relativity treats spacetime as smooth and classical. Matter and energy influence its curvature, and that curvature determines how objects and light move. Quantum mechanics, meanwhile, tells us that physical systems can occupy superpositions, possess unavoidable uncertainties, and behave in ways that have no exact classical counterpart. If matter is quantum, and matter affects spacetime, then it seems reasonable to suspect that spacetime itself must eventually require a quantum description too. In most ordinary situations, this problem can be safely ignored. The gravitational field around Earth is weak enough that general relativity works extremely well. The quantum behavior of atoms can be studied without needing a full quantum theory of spacetime. But there are extreme environments where the separation becomes much harder to maintain. One example lies inside black holes. General relativity predicts that matter can collapse into regions where spacetime curvature becomes extraordinarily intense. In the classical equations, this can lead toward singularities, places where quantities such as curvature appear to become infinite, and the theory itself signals that its description has broken down. Another example appears when physicists trace the expanding universe backward toward its extremely hot and dense early state. At sufficiently early times, the energies involved become so enormous that both quantum effects and gravity should be important. A theory using quantum matter on a perfectly classical spacetime background is unlikely to be enough. These situations suggest that gravity itself must somehow enter the quantum world. One possible starting point is to consider small disturbances in the gravitational field. In general relativity, gravitational waves are ripples in spacetime geometry. If these weak disturbances are treated quantum mechanically, their quanta would be hypothetical particles known as gravitons. In the simplest description, a graviton would have no rest mass and would possess spin too. That spin value is important because it reflects the mathematical structure expected for a quantum carrier of gravity. The graviton has never been directly detected, and even if one were detected, that would not automatically tell us what spacetime itself is made of. A graviton would represent a quantum excitation of the gravitational field in a weak field approximation, rather like a photon represents an excitation of the electromagnetic field. That is useful, but it is not yet a full microscopic description of geometry. During the 20th century, physicists including Richard Phillips Feynman, Bryce Seligman DeWitt, Steven Weinberg, and many others explored ways of treating gravity using the techniques of quantum field theory. At low energies, this approach is extremely useful. Gravity can be treated as an effective quantum field theory. An effective field theory does not claim to describe nature at every imaginable energy. Instead, it provides reliable predictions within a limited range. This is common throughout physics. A theory can be extraordinarily accurate at the scales where it is intended to work without being the final description of reality. The difficulty arises if general relativity is treated as an ordinary fundamental quantum field theory valid to arbitrarily high energies. When physicists calculate quantum corrections, ultraviolet divergences appear. Ultraviolet in this context refers to behavior associated with extremely short distances and very high energies. In many quantum field theories, divergences can be handled by renormalization using a finite number of measurable parameters. Gravity behaves differently. At successively higher orders in a straightforward perturbative treatment, new types of divergent terms appear. An ever-growing collection of additional corrections would be needed to absorb them. This means that general relativity, treated in this simple way as a fundamental perturbative quantum field theory, is not renormalizable in the same sense as the quantum theories describing the other known interactions. That does not mean quantum gravity is impossible. It means the straightforward approach is probably incomplete. At ordinary energies, gravity can still be described predictively as an effective field theory. The real mystery emerges at extremely short distances. John Archibald Wheeler was among the physicists who encouraged the idea that spacetime itself might behave very differently in that regime. He used the phrase spacetime foam to evoke the possibility that, at incredibly small scales, geometry might no longer appear smooth. The calm, continuous spacetime of general relativity could give way to violent quantum uncertainty. This image is suggestive rather than experimentally established. No experiment has revealed literal foam beneath space. But the broader idea captures the central problem. If the gravitational field is quantum, then distances, areas, durations, and curvature may not remain perfectly definite classical quantities under all conditions. Geometry itself may possess quantum states. A successful quantum theory of gravity would ideally explain what those states are. It might tell us whether spacetime has fundamental degrees of freedom. It might reveal that smooth geometry emerges from something more microscopic. It might show that space is discrete at very small scales. Or it might reveal that the familiar idea of space is not fundamental at all. This is why the question of what space is made of eventually moves beyond the standard model. The standard model can tell us about electrons, quarks, photons, gluons, neutrinos, and the Higgs field. It can describe the quantum vacuum with astonishing precision, but it does not provide a complete quantum description of spacetime geometry. That problem belongs to quantum gravity. And until quantum gravity is understood experimentally, the deepest composition of space remains open. We know that space can curve. We know that gravitational waves can propagate through it. We know that quantum fields exist throughout it. We know that empty regions possess measurable vacuum structure. But whether spacetime itself is continuous, quantist, emergent, or built from some deeper quantum degrees of freedom is still unknown. So the closer we move toward the foundations of space, the clearer the boundary of present knowledge becomes. The question is no longer simply what exists in empty space. It becomes something more fundamental. What is the quantum nature of space itself? If spacetime really does possess a deeper quantum structure, then one natural question appears almost immediately. At what scale would that structure become important? Physics has a remarkably small set of natural scales that emerge when three fundamental ingredients are brought together. Max Carl Ernst Ludwig Planck's constant, which sets the characteristic scale of quantum effects, the gravitational constant, which determines the strength of gravity, and the speed of light, which connects space and time through relativity. When these quantities are combined in particular ways, they produce what are known as the Planck units. Among them are the Planck length, the Planck time, and the Planck energy. These numbers are so extreme that they sit far beyond ordinary experience. The Planck length is roughly 1.6 times 10 to the power of negative 35 meters. A proton is approximately 10 to the power of negative 15 meters across. So the Planck length is around 20 orders of magnitude smaller than the approximate size of a proton. That difference is difficult to picture. If a proton were somehow enlarged until it became roughly the size of the observable universe, a Planck length on the same scale would still be extraordinarily tiny. The Planck time is similarly extreme. It is roughly 5.4 times 10 to the power of negative 44 seconds. This is approximately the amount of time light would require to travel one Planck length through a vacuum. Then there is the Planck energy. Expressed using the energy units common in particle physics, it is roughly 1.2 times 10 to the power of 19 gigaelectronvolts. That is enormously higher than the energies produced in present particle accelerators. The Large Hadron Collider at the European Organization for Nuclear Research can produce proton collisions with energies of thousands of gigaelectronvolts per proton beam. Impressive as that is, the Planck energy lies many orders of magnitude beyond it. This is one reason direct experimental access to quantum gravity is so difficult. The relevant scales may be unimaginably small in distance and unimaginably high in energy. But there is an important warning attached to all of this. The Planck length is often described as though it were definitely the smallest possible unit of space. That has not been established. Physics does not currently know that space is divided into cubes 1 Planck length wide. There is no experimental evidence showing that distance comes in little Planck-sized blocks. The Planck scale is better understood as the scale where our familiar combination of quantum theory and classical gravity is expected to become insufficient. It marks a region where quantum gravitational effects may become important. Why should extremely short distances create such difficulty? Quantum mechanics gives part of the answer. To investigate smaller and smaller structures, we generally need shorter wavelengths. Shorter wavelengths require higher energies, so probing a very tiny region means concentrating a great deal of energy into a very small volume. Gravity then becomes increasingly relevant. if enough energy is concentrated into a sufficiently small region. General relativity tells us that the gravitational field can become extremely strong. Heuristic thought experiments suggest that eventually the attempt to probe an ever smaller distance could create enough gravitational disturbance to interfere with the measurement itself. In extreme versions of this argument, concentrating too much energy within too small a region could lead to gravitational collapse. This does not by itself prove that the Planck length is a hard minimum, but it does suggest that the ordinary idea of measuring smaller and smaller distances may eventually stop working in the simple way we expect. Perhaps geometry itself becomes quantum. One approach that takes this possibility seriously is loop quantum gravity. Loop quantum gravity developed through the work of Abhay Vasant Ashtekar, Carlo Rovelli, Lee Smolin, and many other researchers. Instead of beginning with quantum particles moving on an already existing spacetime background, it attempts to quantize geometry itself. Within this framework, the gravitational field is described using quantum variables. One of the characteristic structures that appears is the spin network. A spin network can be thought of as a mathematical graph consisting of links and nodes carrying quantum information. It should not be imagined too literally as a physical fishing net spread through space. Instead, it represents a quantum state of geometry. In loop quantum gravity, operators corresponding to quantities such as area and volume can have discrete spectra. That means certain geometric measurements can take values from specific sets rather than varying in an entirely continuous way. This is one reason loop quantum gravity is sometimes described as suggesting that space is granular. But even here, the picture requires care. The theory does not simply claim that ordinary space is made from tiny cubes. Its quantum geometry is more abstract than that. Another proposal takes discreteness in a different direction. Raphael Dolnik-Sorkin and other researchers developed causal set theory. Causal set theory explores the possibility that continuous spacetime emerges from a fundamentally discrete collection of events. These events are linked by causal relationships. In broad terms, the theory asks whether the familiar smooth spacetime of general relativity might arise from something more basic that preserves which events can influence which others. Distance and geometry would then emerge at larger scales from this underlying causal structure. A different approach is causal dynamical triangulations. Renate Loll, Jan Ambjorn, Jerzy Jurkiewicz, and collaborators developed this framework as a way of constructing quantum spacetime from simpler geometric building blocks. The method uses small pieces of spacetime geometry, arranged according to carefully defined rules. Quantum possibilities for these structures are then combined. Remarkably, under appropriate conditions, large-scale spacetime with familiar dimensional behavior can emerge from the calculation. Again, this does not mean the universe has been experimentally shown to consist of literal triangles or tetrahedra. The building blocks belong to the mathematical formulation of the theory. The hope is that they capture something about how smooth spacetime might emerge from a deeper quantum description. These different approaches share an important motivation. General relativity describes spacetime as continuous and smooth. Quantum gravity may require that this picture changes at extremely small scales. Perhaps area and volume become quantist. Perhaps spacetime is built from discrete causal events. Perhaps smooth geometry emerges statistically from more fundamental ingredients. Or perhaps every one of these ideas will eventually turn out to be incomplete. At present, none has received decisive experimental confirmation. No measurement has revealed a grainy structure of space. No experiment has shown that geometry comes in indivisible units. no detector has found evidence that physical spacetime is literally composed of Planck-sized pieces. That uncertainty is important. The Planck scale tells us where our current theories are likely to become deeply challenged. It does not tell us what waits there. What it does offer is a boundary, a scale so far removed from ordinary experience that the smooth space surrounding us may no longer be the right language. At familiar distances, space appears continuous. At the Planck scale, that assumption may fail. And if it does, then what we call empty space could be only the large-scale appearance of a much deeper quantum geometry. One of the most intriguing possibilities in modern physics is that space may not be fundamental at all. It may be something that emerges. That idea sounds strange, because space feels like the most basic thing imaginable. Everything we know appears somewhere. Every object has a location. Every journey covers a distance. Every star, planet, atom, and particle seems to exist inside an already present arena. But physics has discovered many examples in which something that looks fundamental at one scale turns out to be the large-scale behavior of something deeper. Temperature is not a basic substance. It emerges from the collective motion of enormous numbers of particles. Pressure emerges from countless microscopic collisions. A solid surface feels continuous even though it is built from atoms separated by comparatively large amounts of empty space. Perhaps space-time works in a similarly surprising way. One attempt to reach beneath the familiar picture is string theory. In ordinary quantum field theory, fundamental particles such as electrons and quarks are treated as point-like excitations. String theory replaces that idealized point-like description with one-dimensional quantum objects known as strings. A string can vibrate in different ways. Different vibrational states can then appear at larger scales as different kinds of particles. In this picture, what looks like an electron and what looks like another fundamental particle may arise from different quantum states of the same basic type of object. Michael Boris Green, John Henry Schwartz, Edward Witten, and many other researchers played central roles in developing modern string theory and superstring theory. One reason the framework attracted enormous attention is that it naturally contains a state with the properties expected of a graviton. That gives string theory a possible route toward combining quantum mechanics with gravity. But string theory does not simply say that ordinary space is made from tiny strings. That is an important distinction. Strings are objects described within a much richer mathematical framework involving geometry, quantum fields, and often additional spatial dimensions. In many versions of the theory, more dimensions are required than the three familiar dimensions of everyday space. The extra dimensions may be compactified, meaning they are arranged in a way that makes them extremely difficult to notice at ordinary scales. So the relationship between strings and the space we experience is much more complicated than replacing atoms of matter with strings of space. A different clue emerged from the study of black holes. Black holes brought together gravity, thermodynamics, and quantum theory in an unexpected way. The entropy associated with a black hole turns out to scale with the area of its event horizon rather than with the volume enclosed by that horizon. That observation encouraged a remarkable idea. Gerardus Hooft and Leonard Susskind developed what became known as the holographic principle. Broadly speaking, the holographic principle suggests that in certain gravitational systems, all of the information describing a region may be represented by information associated with a lower dimensional boundary. The name comes from ordinary holograms, where a two-dimensional surface can encode information that produces the appearance of a three-dimensional image. The gravitational version is far more mathematical, but the analogy captures the surprise. A world that appears to contain an extra spatial dimension may in some circumstances have an equivalent description using fewer dimensions. This idea became much more concrete through work by Juan Martin Maldacena. Maldacena proposed a relationship now called the anti-de Sitter conformal field theory correspondence. It provides a precise example of what is known as holographic duality. On one side of the correspondence is a theory containing gravity in a particular higher dimensional spacetime known as anti-de Sitter space. On the other side is a quantum field theory without gravity defined on the lower dimensional boundary of that spacetime. The remarkable claim is that the two descriptions can encode the same underlying physics. A gravitational universe can, in this specific setting, be mathematically equivalent to a non-gravitational quantum theory living in fewer dimensions. This creates an extraordinary possibility. Perhaps space-time geometry can emerge from quantum physics that does not initially contain gravity in the familiar sense. The relationship between geometry and quantum information became even more striking through work by Shinsei Ryu and Tadashi Takeyanagi. They discovered a formula connecting quantum entanglement in the lower dimensional field theory with geometric areas in the corresponding gravitational spacetime. Quantum entanglement describes correlations between parts of a quantum system that cannot be reproduced by treating each part as completely independent. The Ryu-Takeyanagi relationship suggests that the amount of entanglement in one description is directly connected with geometry in another. This led researchers including Mark van Ramsdonk to explore an even deeper possibility. Perhaps quantum entanglement is not merely something that happens within space. Perhaps patterns of entanglement help give rise to the connectedness of space itself. In simplified theoretical settings, reducing entanglement between parts of a quantum system can correspond to spacetime becoming more weakly connected. Increasing or reorganizing entanglement can correspond to changes in geometry. This has encouraged the idea that smooth space might emerge from a deeper network of quantum relationships. If something like this were true of our universe, then asking what space is made of might be a little like asking what temperature is made of. The answer would not necessarily be another tiny material ingredient. Space could be a collective description. Geometry could emerge from information, entanglement, or some more fundamental quantum degrees of freedom. This remains an active area of research, and the limitations matter. The anti-de Sitter conformal field theory correspondence is best understood in specific theoretical settings. Anti-de Sitter space has a different large-scale geometry from the expanding universe we actually observe. Our universe appears, on large scales, to be undergoing accelerated expansion. So physicists cannot simply take this correspondence and declare that the microscopic structure of our own spacetime has been solved. It provides a powerful example showing that gravity and spacetime geometry can emerge from a seemingly different quantum description that is not the same as proving that our universe works in exactly this way. The same caution applies across quantum gravity. String theory remains unconfirmed experimentally. Loop quantum gravity has not been decisively confirmed. Causal set theory has not been decisively confirmed. Causal dynamical triangulations have not been decisively confirmed. Holographic ideas have revealed deep mathematical connections, but they have not yet supplied a complete experimentally verified account of the spacetime surrounding us. So the most accurate answer must remain carefully divided between what is known and what is still possible. We know that apparently empty space contains quantum fields. We know that those fields possess vacuum states and measurable quantum structure. We know that spacetime geometry is dynamical according to general relativity. What we do not yet know is whether smooth space is fundamental. It might emerge from strings, It might emerge from discrete quantum geometry. It might arise from causal relationships. It might be connected with quantum entanglement and information. Or the correct description may involve something that has not yet been imagined. The deeper we look, the less space resembles a simple empty container, and perhaps the strangest possibility is that the space surrounding us is not one of reality's basic ingredients at all. It may be what something deeper looks like from far enough away. So what is space actually made of? The most accurate answer begins with an important distinction. There is a difference between asking what exists in empty space and asking what spacetime itself fundamentally is. Physics has become remarkably good at answering the first question. The second remains open. For Isaac Newton, space was essentially an absolute background. Objects moved through it, forces acted across it, and time passed independently. That picture began to change as fields became central to physics. Michael Faraday and James Clerk Maxwell showed that electric and magnetic fields could extend through regions containing no ordinary matter. Then, Albert Einstein and Hermann Minkowski transformed the discussion again by combining space and time into spacetime. With general relativity, spacetime became more than a passive stage. Its geometry could curve, it could influence motion, it could change in response to matter and energy. It could even carry gravitational waves across the universe. Then quantum physics changed our understanding of matter itself. Particles stopped behaving like tiny classical objects following exact paths. Quantum mechanics introduced wave functions, probabilities, uncertainty and states that could not be described using ordinary classical intuition. Quantum field theory went deeper still. Instead of treating particles as the most fundamental ingredients, it described nature in terms of quantum fields. The electromagnetic field, the electron field, quark fields, the gluon field, the Higgs field, and the other fields appearing in the Standard Model. What we call particles are excitations of these fields. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. The fields themselves remain part of the theory even when no corresponding particles are present. So imagine removing everything visible from a region of space. No atoms, no dust, no light, no free electrons, no detectable particles at all. Quantum field theory does not leave behind absolute nothingness. The quantum fields remain, and they possess a lowest energy state. That state is the quantum vacuum. The vacuum is not simply an empty hole in reality. It has quantum structure, it has correlations, it participates in measurable physical effects. The Casimir effect shows that altering the boundaries around the electromagnetic field can produce a measurable force. The Lamb shift reveals tiny changes in atomic energy levels caused by interactions with the quantist electromagnetic field. Vacuum polarization changes the effective behavior of electromagnetic interactions. Spontaneous emission reflects the coupling between excited atoms and the quantum electromagnetic field. All of these effects tell us something important. Empty space is not empty in the classical sense. But even here, popular descriptions can become misleading. Quantum fluctuations should not be imagined as a literal storm of particles endlessly appearing from nowhere. Virtual particles are useful elements of certain calculation methods, not ordinary detectable objects permanently filling every point of space. Zero-point energy describes features of quantum ground states, but it does not mean that the vacuum is simply an unlimited reservoir of extractable energy. The real quantum vacuum is subtler than the familiar picture of a bubbling cosmic foam of particles. The Higgs field adds another layer. its lowest energy state has a non-zero vacuum expectation value. So even in apparently empty space, the Higgs field does not simply vanish. The vacuum associated with a strong nuclear interaction is more complicated still. Quark and gluon fields interact strongly at ordinary hadronic scales, giving the quantum chromodynamic vacuum a rich structure connected with confinement, symmetry breaking, and much of the mass of ordinary matter. And yet none of this establishes that space itself is made of quantum fields. That distinction is essential. In the usual formulation of quantum field theory, the fields are defined within spacetime. Spacetime tells us how events are arranged. Quantum fields describe matter and interactions within that geometric structure. General relativity makes the relationship more intimate because the energy and momentum carried by fields influence spacetime curvature, while the geometry influences how those fields evolve. But interaction does not automatically mean identity. The Standard Model does not tell us that spacetime is composed of electrons, photons, Higgs fields, or any other known quantum field, and general relativity does not tell us what microscopic ingredients geometry might possess. That is where quantum gravity enters. At the Planck scale, quantum effects and gravity are expected to become inseparable. The Planck length is roughly 1.6 times 10 to the power of negative 35 meters. But that number does not prove that space is divided into Planck-sized pixels. It tells us roughly where our familiar descriptions are expected to become inadequate. Different approaches attempt to describe what may lie beneath smooth spacetime. Loop quantum gravity explores quantist geometry. Causal set theory considers discrete events connected by causal relationships. Causal dynamical triangulations investigates whether large-scale spacetime can emerge from more fundamental quantum geometric structures. String theory replaces point-like particles with one-dimensional quantum objects and provides a framework that can include gravity. Holographic ideas suggest that gravitational spacetime may sometimes be equivalent to a lower-dimensional quantum description. Research connecting quantum entanglement with geometry raises the even stranger possibility that space itself may emerge from deeper quantum relationships. But none of these ideas has yet been experimentally confirmed as the fundamental description of our universe, so the final answer has to remain carefully divided between what physics knows and what it suspects. What exists in empty space? Quantum fields, a quantum vacuum, measurable correlations and interactions, a Higgs field with a non-zero vacuum value, strong interaction vacuum structure. And all of this exists within a dynamical spacetime geometry described extraordinarily well by general relativity. What is spacetime itself made of? We do not yet know. It may be continuous all the way down. It may be quantist. It may emerge from information or entanglement. It may arise from discrete quantum geometry. It may have deeper degrees of freedom that current theories have not discovered. Or perhaps asking what space is made of is not quite the right question, because space may not be a substance assembled from smaller pieces in the way matter is. That is what makes the mystery so interesting. The emptiness between objects hides two very different levels of physics. One is already understood with astonishing precision. The quantum vacuum is rich, structured, and experimentally real. The other remains unfinished. Beneath the fields, beneath the vacuum, beneath the smooth geometry we experience every day, physics still does not know whether space has a deeper foundation. So according to quantum physics, empty space is certainly not nothing. But what space itself ultimately is may be one of the most fundamental questions nature has not yet answered.